Have you ever noticed how when you're tackling a really tough problem, your brain doesn't just, stick to one single idea?
Right. It's more like you're exploring several possibilities at once, isn't it? Looking at different angles.
Yeah, exactly. And then you sort of bring all those threads together. It feels pretty intuitive, this kind of parallel thinking.
hmm It's a really powerful cognitive tool. It stops us from just jumping on the first idea we have, which might not even be the best one. It helps structure our reasoning.
Okay, so that brings us to large language models, LLMs. Getting them to do this kind of complex adaptive reasoning, this parallel thinking, well, that's been a real challenge.
It has. They're fantastic at sequential stuff, following one step after another. But thinking in multiple parallel tracks simultaneously, that's different.
Which is why there was a bit of buzz recently around Google's Gemini, right?
Mhm.
Part of its success, especially in things like the Math Olympiad, was apparently down to this.
That's the claim, that it uses a form of parallel thinking. And it's interesting because it suggests a move closer to how we think.
So today, we're going to dive into a technical report about something called Parallel-R1. It's described as the first reinforcement learning framework designed specifically to teach LLMs this parallel thinking skill, basically from scratch.
The idea is to give these models a more direct path to becoming, let's say, more well-informed in their problem solving,
Hmm.
more robust.
We'll look at how they actually trained it, how the LLMs do parallel thinking during inference, and some findings about how their strategies actually change over time, which I found really fascinating.
Yeah, let's get into the why and what first. Why is this parallel thinking important for an LLM?
Well, you touched on it, the human connection. We naturally use divergent thinking, considering many options. It stops us getting locked into one potentially bad path too early.
Right. And with LLMs, the traditional training methods, mostly supervised fine-tuning or SFT, they have limitations here.
How so?
Well, SFT is largely about imitation. The model learns by copying examples it's shown, so it might learn the pattern of a solution, but not necessarily the underlying reasoning skill in a generalizable way.
Like learning facts by heart versus actually understanding the concept.
Pretty much. It can be superficial. Reinforcement learning, or RL, offers a different path. It's more exploratory. The model learns through trial and error, guided by rewards.
So RL seems like a good fit for teaching a complex skill like parallel thinking.
hmm
But there's a catch.
There is. It's called the cold start problem. If the model has never seen or generated parallel thinking structures before, how do you even begin to reward it? It doesn't know what to try.
Okay, so how did the Parallel-R1 researchers define parallel thinking for an LLM? What does it actually look like in the model's output?
They broke it down into two stages, inspired by how we might tackle problems. Stage one is exploration.
Exploration.
Yeah. When the model hits a point in its reasoning where it's maybe uncertain or sees multiple ways forward, what they call a critical step, it pauses its main line of thought.
Okay,
And then it launches several independent reasoning threads. These are marked out clearly in the text with special tags like path for each separate line of reasoning.
got it.
Yeah.
So it branches out. What's stage two?
Stage two is the summary. After exploring those different paths, the model brings it all back together. It looks at the insights from each path, resolves any conflicts, and creates a concise summary marked with summary. Summary.
And then it continues with the main problem.
Then it resumes its main reasoning chain, but now it's informed by that exploration and summary.
Can you give a quick example, maybe with a math problem?
Sure. Imagine the LLM is working through, say, an algebra problem, step, step, step. Then it reaches a point where maybe two different formulas could potentially apply.
Okay.
Instead of just guessing one, it emits a special tag, parallel. That's the signal.
Right.
Then it might generate two path blocks. Path 1 explores using formula A. Path 2 explores formula B. It follows each path for a bit. Then it generates a summary, maybe saying path A seems more direct, or both paths lead here, but path B is less prone to error. And then it continues solving the problem using the insights from that summary.
Okay, that makes the process much clearer. So it's a structured way to explore and then consolidate.
That's the idea. Now, the big challenge was actually teaching the model to do this, overcoming that cold start problem you mentioned.
Because getting good examples of complex parallel thinking is hard.
Very hard. You can't just easily write thousands of examples for really difficult problems.
So how did Parallel-R1 tackle this? This is the progressive curriculum part.
Yes, a three-stage progressive approach. And it cleverly uses a data pipeline that's actually quite simple and scalable. Stage 1 is the cold start stage.
Okay.
They used supervised fine-tuning, but critically, they focused on easy math problems like the GSM 8K dataset. And they found something really interesting.
Oh, what was that?
A powerful base model, when prompted in a certain way, could actually generate valid parallel thinking traces for a high percentage, over 80% of these simple problems.
Ah, so it could do the format on easy stuff.
Right. But when they gave it the exact same prompts for hard problems, like from the DAPO dataset, the success rate dropped to 0. Absolutely none.
Wow. Okay. So that told them where to start.
Exactly. Start with the easy stuff where the model can already grasp the basic structure. So stage 1 uses this automatically generated data from simple problems just to teach the model the format, the parallel, path, summary tags.
Just getting the syntax right.
Pretty much. Then comes stage 2, RL on easy math. Small-scale reinforcement learning.
So now it knows the format, but maybe doesn't use it well.
Exactly. The behavior isn't stable or necessarily helpful yet, so they use an RL algorithm, GRPO, group relative policy optimization, still on those easy math problems.
And what's the goal here?
To reinforce the correct use of the format. They started with a very strict reward. You only get a positive reward, +1, if the output uses at least one parallel thinking block and gets the final answer correct. Otherwise, it's a penalty, medals 1.
Tough teacher.
Yes, very focused on linking the structure to success, even on simple problems.
Okay, so SFT on easy math for format, RL on easy math for basic behavior. What's stage 3?
Stage 3 is RL on general math, large-scale RL. This is where the training wheels come off somewhat.
Moving to the hard problems.
Yes, using challenging data sets like DAPO. Here, the main goal shifts to just improving overall task performance. The reward is primarily based on getting the final answer right. The assumption is the model now has the parallel thinking skill in its toolkit, and it needs to learn when and how to apply it effectively on complex tasks.
That progressive structure makes a lot of sense. Building up the skill layer by layer.
It seems to be the key to overcoming that cold start issue. Now, digging a bit deeper, the way they designed the rewards, especially in that later RL stage, was crucial.
Ah, the secret sauce. How do you encourage parallel thinking without hurting the model's ability to just solve the problem?
It's a balancing act. They ran some ablation studies, basically, trying different reward setups to see what worked best.
What did they find?
Well, if they rewarded only for accuracy, just getting the right answer, the model got pretty good scores on some tests, like almost 70% on one called AIME 23. But it barely used parallel thinking. The parallel ratio was super low, like 13%. It just didn't naturally choose to use this more complex strategy if only accuracy was rewarded.
Okay, so what if they rewarded only for using the parallel structure?
Then the parallel ratio shot up, over 80%. The model definitely responded to the incentive.
But the accuracy?
Took a nosedive. AIME 23 accuracy dropped almost 10 points. It started prioritizing the form of parallel thinking over getting the answer right. Not ideal.
So neither extreme worked perfectly. What did?
The winner was an alternating accuracy parallel strategy. They switched the reward focus during training. For, say, 80% of the training steps, reward was based purely on accuracy. But for the other 20%, they used a tiered reward specifically incentivizing parallel structures.
Ah, mix.
Yeah, and this seemed to hit the sweet spot. It boosted the parallel ratio significantly up to 63%, but without sacrificing overall performance. In fact, on some really hard benchmarks like AIME 25, this alternating strategy actually beat the pure accuracy approach.
Interesting. So explicitly encouraging the structure, but not all the time, actually led to better results on tough problems.
It suggests that encouraging that structured exploration helps the model find better solutions sometimes. They also looked at architectural variations.
How the model itself was built.
Sort of. One version, Parallel-R1 scene, just used the standard LLM architecture with their RL training, no special modifications.
Yeah.
It actually performed best on average across the benchmarks, about 49% average accuracy.
Huh. So maybe don't mess with the architecture too much.
It seems that way, at least in this RL context. The other version, Parallel-R1 Unseen, did have architectural changes. Things like special masks to try and keep the parallel paths more separate in the model's attention mechanism.
Conceptually, that sounds like it might help enforce the parallel structure.
You'd think so. But counterintuitively, adding that early RL stage on easy math actually hurt the structured model's performance on the harder tasks later on. It dropped by over 8% on average.
Why would that be?
The thinking is that the specific attention patterns or masks it learned on easy problems didn't generalize well. What works for simple arithmetic might actually hinder reasoning on complex geometry or algebra.
That's subtle. So the standard architecture, trained with the right RL curriculum and reward, was the most robust.
That's what the results suggest. But beyond the how, one of the really cool insights was how the model's use of parallel thinking changed over time.
You mentioned this earlier. How do they track that?
They looked at where in the reasoning process the model tended to insert that parallel block. Was it early on or later?
And they saw a pattern.
A very clear one. In the early stages of training, when the model wasn't yet very good at the core task, it used parallel thinking much earlier in the process.
Like it was stuck and needed ideas.
Exactly. It was acting as a computational exploration strategy, like, I'm not sure what to do here, let me try a few different things in parallel and see what happens. A high-variance approach.
Okay, so that's early training. What happened later as the model got better?
As the model became more proficient, this strategy shifted. It would often generate a main solution path first, the one it was most confident about.
Right.
And then often, right near the end of the reasoning chain, it would deploy the parallel block.
Why then? To check its work.
Precisely. It shifted to using parallel thinking for multi-perspective verification. It had an answer it felt good about, and now it was using the parallel paths to double-check it from different angles, to confirm its reasoning and reduce the risk of being wrong, maximize that reward chance.
Wow. So the model learns not just the mechanic, but when to use it strategically, and that strategy evolves.
It really seems to. It adapts its use of the tool based on its own confidence and competence.
This leads to another really interesting idea they explored, using parallel thinking almost as a temporary tool during training itself.
Yeah, this relates to a common challenge in reinforcement learning exploration versus exploitation. You need the model to explore enough different strategies to find good ones, but not get stuck exploring forever.
So the hypothesis was,
Could parallel thinking itself act as a structured exploration mechanism? By forcing the model to generate these multiple parallel paths, especially early on, could you push it to explore a wider range of reasoning strategies than it might otherwise?
like, forcing it to think outside the box, literally by creating boxes for different thoughts.
Kind of. So they tested this with a specific two-stage curriculum just for this experiment.
How did that work?
Stage 1, the exploration phase, lasted for the first part of training. During this phase, they used that alternating accuracy parallel reward to strongly incentivize generating parallel structures. Keep the parallel ratio high, force exploration.
Okay, lots of parallel paths being generated.
Then, stage 2, the exploitation phase. They switched the reward completely to accuracy only. No more direct incentive for parallel structures. The model was now free to use whatever strategy worked best to get the right answer, refining the promising avenues it found during stage 1.
And what happened to performance?
This is the kicker. In stage 2, the model's performance shot up significantly. On that tough AIME 25 benchmark, accuracy peaked at 25.6%, which was much higher than they achieved otherwise.
Even though it wasn't being explicitly rewarded for parallel thinking anymore.
Right. And interestingly, its actual use of the explicit parallel structure often decreased in stage 2.
So the forced parallel thinking in stage 1 acted like scaffolding.
That's the perfect word for it. It served as a temporary scaffold, pushing the model to explore more broadly early on, which ultimately led it to discover more robust and higher-performing reasoning strategies later, even if those final strategies didn't always involve the explicit parallel tags.
The process of parallel thinking during training improved the final outcome, even if the final outcome didn't always look like parallel thinking.
Exactly. The value wasn't just in the final structure, but in the learning journey it enabled.
So wrapping up, Parallel-R1 seems like a pretty significant piece of work. The first RL framework for this, that clever progressive training.
Absolutely. Bootstrapping the skill from easy problems, separating format from behavior, then generalizing, and demonstrating clear accuracy gains on tough math problems.
And those insights into how the model learns the shift from exploration to verification, the whole scaffolding idea.
Yeah.
That feels important beyond just this one technique.
It really does. It suggests we're moving towards ways of training LLMs that are less about just mimicking data and more about instilling deeper, more adaptive reasoning processes, teaching them how to think more effectively.
It definitely feels like a step closer to models that reason in ways that are, well, a bit more like us.
Which brings up a fascinating question to think about, doesn't it?
Go on.
If deliberately scaffolding parallel thinking during training can unlock this higher performance, What other fundamental strategies from how humans solve problems, things like analogy, abstraction, maybe even structured debate within the model, could we potentially scaffold into LLM training?
Could we use temporary structures or incentives during training to push models towards even more sophisticated forms of intelligence?
It's certainly something to ponder. What other cognitive tools could we help them develop?
A really interesting thought to leave things on. Thanks for breaking all that down.
My pleasure. Fascinating stuff.